Yeah.
In this boundary condition, Neumann or J,
Yes.
we find this relation between alphas and alpha tildes.
Yes.
And then we construct the boundary states or the spectrum by demanding that like for Neumann case alpha mu n minus alpha tilde mu n on the state equal to 0. Because
okay, so you are not doing boundary state right now. That's a different approach altogether, right? That tells you what kind of closed string source it produces. Right now, you are just constructing the open string spectrum, right? What you are thinking of is the what closed string background it produces. Okay? So that's what you are trying to analyze now. Okay? In the open string sector, we saw that alpha tilde mu n and alpha mu n, they get related, right? In closed strings, what you are saying will happen that there is a difference alpha mu n minus alpha tilde mu minus n will annihilate the state, but that's not what we are studying here. Okay? This is a spectrum of open strings on the T-plane. This is okay. Any other question? Okay, so let's look at the NS sector. In the NS sector, one can construct a state as follows. You have psi mu, so the C tilde e to the minus phi psi mu e to the, yeah, that's it. So because it's only, there's no C tilde in fact, because C and C tilde are related, right? C. Okay, this is the way we constructed massless states for closed string, except that there we are doubled. Okay, both on the left and right. Here you have only one sector because C tilde is related to C, and similarly phi tilde is related to phi, psi tilde is related to psi. And then the physical state condition we have to impose for BRST invariance demand that K dot zeta equal to 0. Okay. And we should remember that K is along the Neumann direction. But before I forget, let me just tell you that next Tuesday there will be no class. I'll send out a message, but next Tuesday there will be no class. So K is along the Neumann direction. So this means that for zeta in the Dirichlet direction, perpendicular to the brane, there is no constraint. And so this gives you 9 minus P massless fields. And one can also see what representation they belong to. So let's recall that the symmetry group, the original Lorentz symmetry group becomes SOP, 1 times SO9 minus P. Okay. So these 9 minus P massless fields, because they carry index only along the transverse directions, so they are singlet of this. And here it's a vector representation. Okay, so they are Lorentz invariant. So from the point of view of the P plus 1 dimensional world volume theory, they are scalars. Okay. But the number of such scalars is 9 minus P. Okay. And these represent the transverse motion. So these represent the freedom of translating the brane in the transverse direction. Okay, this is in fact what tells us that this brane is a dynamical object. Okay, that given this brane, we can move it. Okay? So moving it will correspond to giving a vacuum extraction value to the scalar fields. Okay, that will be the overall translation of the brane. The other set of massless fields are when zeta is parallel to the brane. So here you have to impose this condition. Zeta dot k equal to 0. Or I should have said that k square, of course, has to be 0, right, for these to be physical. Zeta dot k equal to 0, and these represent massless U1 gauge fields. From the brane. Okay, so this tells us that a D brane in superstring theory carries a massless U1 gauge field living on it. Okay, which is somewhat unusual. Otherwise, the D branes are like normal soliton solutions. In a quantum field theory, you can construct solutions where the energy density is localized along some subspace, right? Which you can think of as branes, right? Like, for example, you can have point-like objects, which have collective motion in the transverse directions. Okay? But having gauge field living on the brane is very special to D branes. Right? Typically, in quantum field theory, if you construct such soliton solutions, you don't have gauge fields living on them.
Even though you are saying that these represent the freedom of translations, the massless ones,
Yes.
scalars of SOP, y, you also mean rotation, right? In some sense, like because it's a vector of SON minus P, 9 minus P.
Yes, this is a vector in the transverse direction, right?
Yes.
So if you suppose the brane is positioned at x equal to 0, right? X transverse equal to 0. And you move it to a position A.
Yeah.
That A will transform as a vector of SO9 minus P. Okay?
Yeah, but that means you can rotate it also.
You can rotate it also, but rotating will mean that you have to give phi the scalar field of a expectation value that is linear in the axis. Right? Imagine that you have a brane like this, right? If you rotate it, then the farther away you go, the more is the displacement, right?
Yes.
Okay, so that will correspond to having the scalar field being linear, a solution where you pick a linear in X.
Yeah.
Right? It's sort of, yeah, I mean, typically when you talk about massless, when you try to characterize the modes, you use delta function normalizable modes, right? These are not delta function normalizable because they grow as as x goes to infinity. Okay? So that's why you don't consider them as new modes, yeah, but you can certainly construct solutions where the scalar fields are linear, right? That will correspond to brane being rotated. Okay, but you don't think of this as a new field, right? It's the defined vacuum expectation value of the old field, right? Where you take the scalar field to be linear rather than constant.
And here we are by brane always brane world volume. We are considering
Brane world volume, yes. Exactly.
And there we are seeing
On that, we are seeing massless fields. Exactly. So if you have a string, for example, suppose P was 1, right? Then it's like a string. Right? And the massless fields are the ones. So suppose you have a plane wave of these massless fields, right? What does the plane wave represent? The plane wave will represent the oscillation of the string. Okay? This tells us that the string can oscillate in the transverse direction. Okay, that's like a normal string can oscillate in the transverse direction, right? Similarly, if you have a membrane, right? Membrane can also oscillate in the transverse direction, and the corresponding scalar fields will be these. Yeah, exactly. So as far as this part is concerned, it's the same as in bosonic string theory. The only advantage is no tachyons in this case.
kinetic term for the massless fields.
Yes, there will be, right? when you write if you write a string field theory action, there will be indeed be a kinetic term for this massless fields. If you just do worldsheet analysis, okay, then you can calculate the S matrix, and then you can, from that S matrix, you can ask what kind of effective field theory will produce that S matrix, and that will also have a standard kinetic term for the scalar fields.
So people call this modularized, right?
Yeah, exactly.
And I would think that modularized would have, I mean, they are just an integral in the end.
No, moduli fields in 3+1 dimension, moduli fields are scalars which have no potential. So that you can give them arbitrary vacuum expectation value and they can remain there, right?
Different from the moduli we see in testing theory, the modular of the matter.
Yeah, that's right. So that, I mean, because moduli, okay, it's not different. The reason they are called moduli is because they parameterize the vacuum manifold. Vacuum manifold by definition is independent of space-time independent configurations, right?
Yeah.
Okay. So in that sense, they are called moduli of the vacuum manifold.
So like choosing a web for each phi.
Exactly.
Classless field will be like choosing a web.
Exactly, right?
And,
And the physical interpretation of that will be that you just you have translated the d-brane somewhere in the transverse direction.
okay. And I can do perturbation theory around that.
You can do perturbation theory around that vacuum, right? And the perturbative spectrum will always contain massless fields, because instead of moving the brane at one go, right, you can set up an oscillation on the brane. Okay, this is like a normal string, right, or a membrane. Okay, so you also have Ramon's vector. Massless states. We're not talking about fields here. Okay, here you have C to the minus 5 S. Okay, let me write it. Okay, where this is a spin field. And total dimension, you can again check that it adds up to 0 because this is dimension 5/8. This is dimension 3/8. And this is dimension -1. So there are massless fermions that live on the brane orbital. So these massless fermions have two different interpretations. Both are correct. One is that because the brane preserves certain supersymmetry, we'll see that the brane does preserve some supersymmetry. Okay. Then those supersymmetries that are not broken by the brane, right, they will pair the bosonic modes which are there, which are the U1 gauge fields as well as the scalars, with fermions. Okay. So you can think of these massless fermions as being superpartners of the bosons which are there, right, scalars and vectors. The other interpretation of this is that we will see that the brane breaks half of the supersymmetry. Okay. So if the brane breaks half of the supersymmetry, okay, there should be Goldstone bosons associated with the broken supersymmetry. Okay. In fact, sorry, Goldstone fermions, because supersymmetry is a fermionic symmetry. So, okay, maybe I can go back here. Right. See, here we see that once you have put a d brane, right, it breaks translation invariance in the transverse direction because you have put x equal to a, right? You have made a particular choice, so translation in that direction is no longer asymmetric. Okay. These scalars, okay, the p 9 minus p scalars, you can also interpret that as the Goldstone boson of the broken translation invariance. right? Because by giving the vacuum expression to the scalars, we move in the transverse direction, right? So there's a Goldstone bosons are the broken translation invariance. So in the same spirit, if some supersymmetries are broken by the brain, that should be Goldstone fermions.
Now you are talking about the world sheet supersymmetry or
No,
target
no, space-time, space-time.
space time?
Yeah. Okay, world sheet supersymmetry we have made use of, and now we can forget about it for now. Okay, so everything is being done at the space-time level. So the claim is that from the space-time perspective, some supersymmetries are broken, and those supersymmetries, so the corresponding broken supersymmetry, you should have transverse motion. Sorry, no, you should have Goldstone fermions, and these are the Goldstone fermions, okay, which are also sometimes called a Goldstenos. Is this okay? Yeah, not otherwise. Both interpretations are correct, right? These fermions you can interpret as superpointers of the gauge fields and gauge fields plus scalars. Right? But you can also interpret this as Goldstone formulas.
Is it easy to visualize how this fit into a multiplet?
All these?
This fermion scalar and the mass distribution.
Yeah, you can work this out. Okay? I mean, you can work a lot of it just by the fact that looking at what bosonic part is unbroken, right? Okay, so these should form representation of that unbroken symmetric group. Yeah, so these will be, as we already saw last time, these will be spinors of the product, right? SOP, 1 times SO9 minus B. Okay, so now we have to understand what kind of supersymmetry this brain has. So for this, let's recall that for all the elementary fields that we have on the worldsheet, right, the psi and x and all, we have to put some boundary condition. Right? That psi tilde equal to psi or minus psi. Similarly, x, whether the sigma derivative of x is 0 or tau derivative of x equal to 0. Yeah, we have to put some boundary condition. Those boundary conditions will imply boundary conditions on any composite fields, any other field that is derived from them. Okay. Now let's look at the field, the supersymmetry generator. Okay, if you remember, sigma A we are defined as e to the minus phi by 2 times SA. Okay, so this is dimension. So the SA is the spin field, matter spin field. So this has dimension 3/8, sorry, dimension 5/8. This is dimension 3/8. So this is dimension 1 current. Okay. And then we have sigma tilde I. Let's work with 2B. So that there's a confusion. Let's suppose you have sigma tilde I, which is e to the minus phi by 2. Phi bar bar 2 S tilde I. So one would expect that the boundary condition, because these are left moving, these are right moving. Sorry, these are right moving, these are left moving. We'll expect the boundary condition at the two ends, at each end, will relate the sigma tilde to sigma I. Okay? And the question is, what is the relation? Okay, what is the relation between sigma tilde and sigma I? Okay. So this is easy to guess for D9 then. So let's start from there. So on the D9 then, here the full SO9, 1 Lorentz invariance is clear. So this basically means that there is really no choice, right? Up to a overall phase, we must have sigma tilde A equal to sigma A at the boundary. Okay, possibly up to a phase. Okay, but the phase can often be absorbed into a redefinition of the spin fields themselves. Okay, because left and right moving spin fields, we can put independent phases. So we can say that on D9 brane, the boundary condition is this. Is this clear? Oh, because how do I mean? That could have a matrix, right? Multiplying it. That matrix will not commute to the Lorentz generator. These are spinor representations, right? So in order that, so whatever boundary condition you put, it has to commute to the Lorentz generators, right? Because after Lorentz transformation, it should have, also satisfy the boundary condition. And what I'm saying, that basically forces the sigma tilde and sigma A to be equal without any matrix. Is this point clear?
These sigmas have to be Lorentz. Whatever I break to, like SOP comma 1.
Yeah,
Spinors.
exactly. SOP comma 1 times SO 9 minus P spinors.
Yeah. And it has to be that as well.
Yeah,
Spinor
it's a spinor of that. Right? So here you am taking P equal to 9. Right? So then the only spinor is only possibility is this, right? Because SO9 comma 1 is preserved. So these are spinors of SO9 comma 1. Right? So how do you relate two spinors of SO9 comma 1? Right? They must be equal at the boundary. Is this clear? So this boundary condition is consistent with SO9 comma 1. Okay. If you try to put a matrix here, in general that matrix will not commute with SO9 comma 1. Now let's, okay, and we can see from here, okay, there are two lessons here. Okay. First lesson is that only half of the supersymmetry is preserved. Because earlier sigma A and sigma tilde were generating independent supersymmetry. Right? But now we see that in the presence of a D brane, both have gotten related. Okay? So D9 brane, right, forces the oscillators of sigma tilde, I mean, if you had an integral of sigma tilde A, right, that is related to integral of sigma A, because they are equal at the boundary. Okay? So instead of having two independent sets of supersymmetries, one from the left, one from the right, okay, we have only one independent supersymmetry, independent set of supersymmetries. Pardon?
When you start doing open string,
Yes.
there you will, when you put the boundary condition at 0 and pi,
Yes.
you see that alpha equal to alpha.
Yes.
So then you see only half the degree. So
Exactly.
this is also similar thing.
This is also similar. Exactly.
This is like epsilon, what is it called? Sigma. Sigma is in the sigma tilde.
Yeah.
Not only at the boundary, like only one is there.
I mean, this is the boundary condition. Then when you decompose into oscillators, right? So all the oscillators will get related, right? So the boundary condition forces the oscillators also to be related, right? But the point is that they are not equal to each other, right? Even for alphas, right? Once you go in the interior, right, the sigma dependence of alpha and alpha tilde are different. So they will be related, but they will not be equal, right? So similarly, sigma and sigma tilde will be related even in the interior, but they are not equal, right? But the important point is that there is only one independent set of supersymmetry generators. Is this clear?
It's not possible to see this sigma tilde equal to sigma from the oscillator things, because this sigma A and sigma tilde A we have in terms of.
Yeah, except that the relation is not easy, right? It's a quantum relation. Because if you recall, sigmas were, you have to first bosonize the size, as e to the plus minus I phi by 2, etc. And then you have to, these are defined as e to the I phi by 2, right? So in principle, you can try to translate the boundary condition on the size to the boundary condition on the phi's, and then from there derive the boundary condition on the sigmas.
We were saying
That will be equivalent to this, right? And that another complication there is that the spinors, right? It depends on what basis you choose, right? E to the plus minus I phi by 2 plus minus I phi by 3, that's one basis, right? You can change basis, right? And so, I mean, it's much easier to just get the relation using Lorentz invariance, right? But in principle, yes, you can translate the boundary condition on psi to boundary condition on the phi's, which are the bosonized size, and then work out the boundary condition on the sigmas.
But here what we have done is that we have taken sigma tilde to be some matrix times sigma, then
Yeah, then it will not be
SO9, 1
invariant, exactly,
It would be invariant only if it is some identity.
exactly, that's right. Half the supersymmetry will still be preserved. Because so D9 brain breaks half of the supersymmetry. The second lesson is
What
that-
you just, hello?
yes.
Yeah, what you just said for the D9 brain, what is so special about D9? I mean, you can just say that for DP brain also, right? That on the on the world volume theory, since these are spinorial on the world volume.
Yes.
So, and you want Lorentz invariance to be present on the world volume, you can give the same argument there, no?
Okay, we are going to do the DP brain in a few minutes. So then it will become clear why things are different.
Okay.
Lorentz invariance will not fix the structure completely. Okay, but the second lesson first, let's go through that. So D9 brain exists only in 2B, 2A, 2B. Okay, because in 2A, these carry different levels, right? One is A, one is A dot, right? If this is A, that is A dot, right? So you cannot set them to be equal, right? They have different Lorentz transformation properties. Okay. Now it turns out that there is a more complicated way of defining D9 brain even in 2A, right? But those will break all supersymmetries and those will also have tachyons, right? So we are not going to go into that right now. Okay, so let's look at the stick to the standard D brains, right? Which preserve half of the supersymmetry, and for these we have this situation that D9 brain doesn't exist in 2A. Now go to the DP brain. Okay, I'll first give the result and then we'll see how to justify it. So on DP brain, what will happen is that sigma, again in 2B, let's do 2B. Sigma tilde A will be given by gamma 1 to gamma 9 minus P AB sigma B for P odd, and we have sigma tilde A dot. Sorry. Yeah, this is it. So this is for 2B and for 2A. So these are gamma matrices in transverse directions. Now, first of all, the fact that I have chosen gamma matrices in transverse direction, that's a matter of choice. I could have taken gamma matrices in the tangential direction. And the reason is that if you take the product of all the gamma matrices, gamma 0 to gamma 9, okay, this acts as identity on the spinor representation, either 1 and -1, right? It acts as 1 on the A and -1 on the A dot, because this is a gamma 5. This is analog of the gamma 5 for the 10-dimensional gamma matrices, right? And these are chiral spinors. So this product, right, has a fixed value, either 1 or -1, depending on what representation you are using. So using that, we can rewrite this in terms of product of gamma matrices in the tangential direction. The important point is that it involves this product of gamma matrices. So this will be consistent with Lorentz with the invariance under this invariance, okay, because that product of gamma matrix, right, commutes with this. Sorry, yeah, sigma A dot B. Thank you. Okay. Now, if you believe this is also telling us, okay, that 2B has only odd branes and 2A has only even branes, because this condition can be written, otherwise you cannot write this, right? Because if you have product of odd number of gamma matrices, right, that connects the dotted and undotted spinors. Okay. The even number of gamma matrices preserve the structure of the spinor, right? It connects even to even and odd to odd. Okay. But odd number of gamma matrices will connect dotted and undotted. Okay. So here, if P is odd, then you have even number of gamma matrices, and that better connect the same kind of index. Okay. So this condition can be written down only in 2B, this condition can be written down only in 2A. So this is just a property of the Lorentz group. So this is telling us that the supersymmetric branes exist only for odd P in 2B and for even P in 2A. Right? So 2A can have 0 branes, 2 branes, 4 branes, etc. Right? And 2A can have D1 brane, D3 brane, D5 brane, etc.
The A is like P comma 1 spinor index.
A is both. You can do either P comma 1 or okay, that A you can think in terms of 9 comma 1. Right? But that product, of course, doesn't commute to the SO 9 comma 1. Right? So it is still a 9 comma 1 spinor, right? That is not a symmetry. So you are supposed to decompose into the irreducible representation, but you can choose to label it by the 9 comma 1 spinor index, right? Okay. And in that form, so this has been written in that language. These are 9 comma 1 spinors, right? But you can clearly see that once you have a condition like this, right, it's not invariant under SO 9 comma 1. Yeah, so it's invariant under this product. Right? It's invariant under SO P comma 1 because those gamma matrices never appear anyway. Right? And it's invariant under SO 9 minus P because this product is invariant under SO 9 comma 9 minus P. Right? If you take the product of all gamma matrices, right, that is like the gamma 5, and that commutes to the Lorentz group. Yeah. Exactly. Yeah.
Can we go back to a 9 comma 1? So
Yes.
there, the statement was that we have to these two have to be equal because of SO 9 comma 1 Lorentz invariance.
Yes.
How, I mean, spinor is an object that transforms under Lorentz transformation as that commutator of gamma mu gamma nu.
Exactly. Yeah.
Then what is the statement?
Yeah. And if we had put some arbitrary matrix here, right? Then the B transforms under the Lorentz group, A transforms under the Lorentz group. Okay. So you get U M U inverse. So the matrix will change.
Okay.
Right? Because U M U inverse is not M. Right? So the boundary condition, if you put a fixed M boundary condition, then under Lorentz group, Lorentz transformation, the boundary condition is going to change.
Okay.
Right? So it's not a Lorentz invariant boundary condition. So you have to choose M once and for all, right? Okay. But now if you go to a different Lorentz frame, if the matrix changes, then there is Lorentz invariance gets broken, right? So that is the statement. Yeah, this also breaks half supersymmetry. Yeah, because sigma tilde A is given in terms of sigma. Right? So this also breaks half supersymmetry. Each P. For each P, yeah, half of the supersymmetry is broken.
So what is this sigma and sigma tilde from the target space perspective? Like on world sheet, it's like holomorphic at our
Yeah, so target space perspective, these are two supersymmetry generators. Because you saw that integral of sigma is what you use to generate supersymmetry transformation, right?
Okay.
So from the target space viewpoint, these are the supersymmetry generators. But now what it is saying is that these integrals are not independent anymore because at the boundary they are related. Is this okay?
This P having or is also related to the fact, I think, that in 2B we have 0 form, 2 form.
Yeah, yeah. So we'll come to that. Yeah, exactly. Right. So you can see that these are also charged. I mean, these are base branes are such they can couple to appropriate Raman-Raman fields.
I think both statements come from this representation theory, like thing on
Yeah.
there also we decompose this.
Yeah, except that you have to first you have to check that those, yeah, so both statements come independently, right? But then to show that this couples to the Raman-Raman field will require more work, right? That will only tell us that the Lorentz structure is such that there is a possibility that the de Bruijns can couple to Raman-Raman fields, but this doesn't prove that it does. Okay, so let me just give a brief outline of how one could possibly derive this. So for this, we'll start from D9 brane and then try to work our way towards general DP. We'll begin with D9 brane. Okay, for which the boundary condition you have chosen to be sigma tilde A equal to sigma A. Okay. So D9 brane, let's label by 0, 1, 2, 3, up to 9. Now, if you recall, the way we define the spin fields, okay, is that we combine psi 0 plus minus psi 1, call this some e to the plus minus phi 1. Or if you just do Euclidean, right? Do Euclideanize. Then plus minus I phi 1, psi 2 plus minus I psi 3 is e to the plus minus I phi 2 and so on. Psi 8 plus minus I psi 9 to the minus I plus minus I phi 5. Now, suppose on the 9th direction, you change the boundary condition from Dirichlet to Neumann. Sorry, from Neumann to Dirichlet. So change boundary condition along X line from N to D. Okay, and you want to see what effect it will have on the boundary condition on the sigmas. Okay. So the changing this boundary condition in the 9th direction locally, right? Suppose you are working at a boundary, okay, can be implemented by saying that we are using minus psi tilde 9 instead of psi tilde 9, right? Because boundary condition is related psi 9 and psi tilde 9. right? You put an extra minus sign, right? So that can be implemented by saying that effectively you are taking psi 9 to psi tilde 9 to minus psi tilde. We could have done this also for the psi, but let's do it for psi tilde. Right? So suppose you want to change psi tilde 9 to plus minus psi tilde 9. So this will have the effect that phi 5 changes sign. So if we are started with a particular spinor, e to the I plus minus phi 1 by 2, this will go to e to the power I plus minus phi 1 by 2. Okay.
Sorry, why is the holomorphic part you are only written?
Sorry, yeah, these are all anti-holomorphic because I'm changing the side. Thank you. Okay. So you see that if we have to find some way, okay, we have to find a CFT description of how to change from this to this, okay, on the spinor representation. Okay. And the claim is that psi 9 zero mode does the job. Okay. So let's look at psi 9, sorry, psi tilde 9, right, which is basically to the I phi 5 minus e to the minus I phi 5, right? One over 2i. Suppose you take the OP of this with any of these, with this one, okay, plus or minus sign. So psi tilde 9 of z with e to the I plus minus phi tilde 1 by 2. The most singular part will come when you pick the part of psi tilde 9 that has opposite sign compared to this, because that will have a z minus z to the half, z to the minus half, right? The other one will have z to the half. So this will go as z to the power minus half on e to the I plus minus phi tilde 1 by 2. Okay, doesn't matter whether you start with plus or minus, it will always flip the sign, right? Up to and times something, times a phase, which you don't worry. Is this clear? But if you look at the expansion of psi tilde 9, it is sum over n psi tilde 9 0, so which we call, I think, b tilde 9 0. Sorry, b tilde 9 n z to the minus n minus half. Okay. So the fact that you pick up the z tilde to the minus half, right, that corresponds to the n equal to 0 term here, right? So this will basically tell us that b tilde 9 0 acting on SA on the state SA 0 on the vacuum gives you the correct state. But B tilde 9 0, if you recall, is the gamma 9, right? The way we got the gammas in the first place, right? It's by noting that the B's satisfy the Clifford algebra, B tildes, okay? And those we identified as the action of the gamma matrices. Okay? So this is telling us, so that tells us that psi tilde 9 acts as gamma matrix. Okay, the gamma 9. Psi tilde 9 acts as gamma 9. Okay? And this analysis is telling us that this change, okay, on the spinor representation is implemented by the psi tilde 9 0 mode, okay, which is gamma 9. Okay? So effectively, if you want to change the boundary condition from Neumann to Dirichlet in the 9th direction, okay, that can be implemented by replacing sigma tilde by gamma 9 on sigma tilde. Is this clear? Because gamma 9 is the 0 mode of psi tilde 9, and 0 mode of psi tilde 9 precisely changes the spinor in such a way that it gives a new boundary condition from the old one. So in other words, every time you change Neumann to Dirichlet, okay, you get the corresponding gamma matrix, multiplying it. Okay, and that's what you see here. Right? If you change from Neumann to Dirichlet along 9 minus p of the transverse directions, you get the corresponding gamma matrices, okay, coming in, acting on sigma. Okay. Order in this case doesn't matter because that's just a sign. Right? And you have not been careful about the signs anyway. Is this okay? Yeah. Here? Yeah. So what I was saying that we see from here that psi tilde 9, if you, so suppose you want to change this to this, right? And you want to do that because that's the new combination that should appear in the boundary condition, right? What it is saying is that the psi tilde 9 0 mode, okay, basically does the job. Because psi tilde 9 z with this, these are 0, gives you z to the minus half times this. Okay. Now apply both on the vacuum. Okay. So that will tell us the psi tilde 9 and psi tilde, use the fact that psi tilde 9 is given by this expansion. Right. So z to the minus half coefficient here is giving the action of b tilde 9 0. Right. So this is telling us that if you apply b tilde 9 0 on this state, right, it will produce this state over here. Right, and b tilde 9 0 you are identifying as a gamma 9. Right, because that's how the gamma matrices entered in the first place, right? By noting that the 0 modes of psi tilde form a Clifford algebra.
If I do a contour integral, I'll get the same.
Yeah, if you do a contour integral, you get the same thing.
1 by zeta.
Exactly. Right, here I'm just comparing the expansions.
The thing on the right in this OP, that is some S tilde B, right? What is?
Yeah.
I mean, what do you want to say with this OP that?
Yeah.
On the left, the z to the minus half term is b tilde.
So this is,
SA.
so this combination, right, is what should appear in the boundary condition. In the boundary condition, right? Earlier it was SA equal to S tilde, right? Now I am saying that the combination, the SA should be the set equal to not S tilde, but this object. And b tilde 9 acts as a gamma matrix. Right? That's all you are saying here.
Yeah, but to say that you need the right hand side to be SA, right? For this OP.
Now, okay. So you can see clearly the right hand side cannot be SA, right?
Yeah.
But if you apply one gamma matrix on S tilde 9,
Yeah, how can it? Oh,
it will change.
yeah, you need SB
undotted to dotted index.
Yeah.
So like right hand side has to SA dot. And that's consistent with the fact that this boundary condition exists only for the for type 2A. Okay. So ideally you should have started on this side as SA dot, right? And it will convert it to SA. Right? It doesn't matter how you put it. right? So to begin with, you allow SA and SA dot everything, right? Just to work out a boundary condition, and then you keep only those which are allowed in the theory, right? So if you find that your boundary condition is relating SA to S tilde a dot, okay, that basically indicates that you are working into A, right? Those kinds of boundary conditions you can only put in type 2A theory. On the other hand, if the boundary condition is relating SA to SA to SB, then we know that we are in the type 2B theory, right? Because those spinors exist only in type 2B. Is that clear?
Dot ones will correspond to having some odd number of lines.
Exactly.
A2 correspond to the even number of.
Exactly, right? Dots will correspond to odd number, right? And then when you apply on this, right, it will give even number, right? Which you can set equal to the even number. See, SA we are not touching at this stage, right? Because you have changed psi tilde to minus psi tilde. You could have also done with on the psi side, right? But you do only on one side because you want to change from Neumann to Dirichlet, right? In the sign on the side where you change, right, the starting spinor, right, will have to have the opposite index, right? Because finally we want to get A, right? So if you had A before, you start with A dot, so that after you apply the gamma 9, you get an A index. Okay, so for D8 brane, right, which is what we have been discussing, the boundary condition should take the form. So for D8 brane, we should have S tilde A dot as gamma 9 A dot B SB. Okay, you can also write this in the other way, right? S B equal to gamma 9 B A dot S tilde A dot. Okay, because this squares to 1. Is this clear?
Which mode will it correspond? Some B0.
B09, B9, B tilde 90. Oh, this one? Yeah, B90. See, you can B9, the 0 mode of B9. Because upon it, you can the change to Neumann from Neumann to Dirichlet, right? Basically tells us that whatever relation was there between psi and psi tilde has changed sign, right? So you can implement it either by changing the sign of psi or of psi tilde, right? So that corresponds to using either gamma 9 or gamma 9 tilde, right? At the end, it really makes no difference. Okay, so all we are doing here is we are saying that if you change the boundary, if you change psi tilde 9 to minus psi tilde 9, then the corresponding spinor changes. Okay, it becomes of the wrong type. Okay. And that basically means that the theory itself has to be the other theory, right? Not 2B but 2A.
This should be sigma.
Yeah, well, sigma you just multiply by yeah, e to the minus 5 by 2, right? That e to the minus 5 by 2 and e to the minus 5 tilde by 2 are equal. That sign you are not changing.
So we are thinking of it like there was D9 brane, there this sigma tilde was S tilde was S. Then we change one direction from Dirichlet to Neumann.
Exactly.
So we have to multiply one gamma.
Exactly. Right? E to the minus 5 by 2 is equal to e to the minus 5 bar by 2. Right? That relation you are not touching.
That way we can argue all this.
Exactly. Right? You can just repeat this now. Right? From
This
D9.
argument was to see that okay, this should be what.
Exactly. That this structure should what come out. Any other question? Pardon? D8 branes for 2A. right? D9 we saw is for 2B, so D8 will be for 2A. So we started with 2B, right, D9, and now we are changing N to D, so it becomes a 2A. Okay, so this kind of boundary condition we can impose only on 2A. Right? We change psi tilde to psi tilde 9 to minus psi tilde 9. And this is what you get. Right? So it's best to think of 2A and 2B together. Right? Imagine that you have both sigma and sigma tilde. Both for sigma you have both dotted and undotted index. And for sigma tilde both dotted and undotted index, right? Only at the end you can decide whether you want to work with 2A or 2B. And depending on that, you put appropriate restriction on the sigmas. Okay, because the worldsheet size, right, when they collide with sigmas, they do change dotted index to undotted index. Right? It's only after you impose the fact that you have to have a GSO even operator, right, that a single psi cannot come by itself. Right? That's the reason why it's consistent to impose the that condition, okay? Because you can either have two psis, right, which will change dotted back to dotted and undotted back to undotted, okay? Or you have a psi and e to the minus phi by e to the minus phi, right? That will change dotted to undotted, or vice versa, but it will also change e to the minus phi by 2 to the minus 3 phi by 2 or e to the phi by 2, right? Where you have seen that the projection rules are different.
So it's like we are taking first D9, right?
Yes.
Neumann boundary condition along all directions. There we have this SA and S tilde.
Yes.
It could be S tilde could be A or A dot depending on 2A or 2B.
Yes.
So first.
But D9 brain exists only in 2B.
So okay, D9 brain exists only in 2A. So there it would be S tilde A equal to SA.
Yes.
By that S
Yes.
9, 1 argument.
Exactly.
Then we change one direction from one boundary condition from Neumann to Dirichlet.
Yes.
That means that will give a 1 gamma 9 factor.
Yeah. So this condition, right, sigma tilde. So basically what it says, sigma tilde A equal to sigma A. Right? This condition will now be replaced. This one, sigma tilde A, will now be replaced by gamma 9 A B dot sigma tilde B dot.
If it's only one direction, then you could change this undotted to dotted.
Exactly. If you change one direction, only one direction, it will change undotted to dotted.
Since 2, then again it will be from.
Exactly. Okay, so this is telling us that the D branes in type 2 exist in with a gap of 2, right? If DP brane exists, then DP plus 2 and DP minus 2 exist, but not DP plus 1 or DP minus 1. Then those exist in the other 2A.
This restriction that you're saying for you need to have even in type 2 and odd in type, this is just for supersymmetric branes.
Yeah, this is for supersymmetric branes.
I can, like, in principle, D8 brane can be put in type 2B, right? By breaking.
Yeah, but those are non-supersymmetric branes, those are tachyons, and those are more complicated to construct.
Is it like a generic fact that when you don't have supersymmetry, you get tachyons?
Yeah, that seems to be a generic fact. It's not, it's not a property that you can prove in general, but typically if you don't have supersymmetric branes, they do acquire tachyons.
Tachyon means open string tachyon.
Open string tachyon, yes. Which basically shows that those are unstable objects.
But here it seems like this, we have one gamma.
We have one gamma, yes. That is true to change from D9 to D8. For D8, you have one gamma.
Yeah.
Right? If you want to now change from D8 to D7,
Then how can it appear there?
the number of transverse directions. Right? Every time you change from N to D, you'll get a gamma.
For P even, I will have odd number of gammas.
Exactly. That's why P even exists in type 2A. Right? For P odd, you have even number of gammas.
This makes sense if we see for G7 brain there will be gamma 1 and
Gamma 1?
gamma 1, gamma 2.
Yes, exactly. Yeah, or gamma 8, gamma 9, depending on where you are. Exactly. Okay, so yeah, we'll try to calculate or at least try to show that these branes carry Raman charge. Okay, but for that you have to, do some extra homework. Okay. So to show that a D brane carries certain charge, right? Whether it's Raman charge or tension, right? Energy, source of energy. Okay. We have to calculate one-point function of something. Right? If you want to calculate, for example, the energy density that the D brane carries, you have to calculate the one-point function of the graviton. Okay? If you want to know what kind of dilaton its source is, okay? You have to calculate the one-point function of the dilaton. Okay? Similarly, if you want to know if it carries a Raman P form charge, okay, then you have to calculate the one-point function of, a DP brane will carry Raman P plus 1 form charge. Is that clear? Because D0 brane, let's start with D0 brane, right? That carries charge under a gauge field, right? Because there is a coupling integral A0 dt, right? You can use. So on a DP brane, right, the wall volume is P plus 1 dimensional, so it should carry a Raman P plus 1 form charge. Okay? So you have to show that the one-point function of the P plus 1 form is non-zero, right? On the in the presence of the D brane. Now, calculation of the one-point function, okay, on the disk, right? In this case, you have an open string wall volume, so you have to calculate the one-point function on the disk. This involves some new challenges, okay, and that's the following, right? So take one-point function on the disk. Now, why disk? That you can start with the genus expansion, right? The leading contribution to any amplitude comes from the sphere amplitude. Okay, that will give you GS to the minus 2, right? Because that comes from GS to the minus 2. But first of all, that of course is supposed to vanish, right? Because of the conformal invariance. You don't fix the SL2C conformal invariance on the sphere. Okay, so when you divide by the volume of the group, it just becomes 0. Okay. In any case, okay, one-point function of the sphere doesn't know about the presence of D branes. Right? So irrespective of whether it vanishes or not, one-point function of the sphere will have no relation to whether there are D branes present or not. Right? Because D branes only affect boundary condition, right? So unless you have a Riemann surface with boundary, you don't know that there is a D brane. Okay? So there may be one-point function on the higher genus surface which doesn't vanish. Right? Those will tell us that somehow the quantum corrections are generating a tadpole. Right? But those are not related to D branes. So the first order, the leading order, where the D brane starts into play, is a disk. Okay? Because disk has Euler number minus 1, Euler number 1. Okay, so it will give you 1 over GS contribution. Okay? So that's why we focus on the one-point function on the disk. Right? There are higher order corrections. One-point function on the annulus will also depend on the D branes, presence of D branes, but the leading contribution will come from one-point function of the disk. Now, one-point function on the disk, the challenge here is the following, that the disk, which is the upper half plane, okay, so disk is equivalent to upper half plane. Okay, just in that as the sphere is equivalent to the full complex plane with points at infinity identified. So disk is equivalent to upper half plane, and this has 3 conformal killing vectors, right? This is SL2R symmetry. So 3 conformal killing vectors. if you insert the 1-point function here, this is the closed string vertex operator, right? This is a closed string vertex operator. That's what we are calculating. 1-point function of this fixes two of the conformal killing vectors because you have to specify the position of this closed string vertex operator. Okay. Imagine that it is at 0, right? You can use SL2R to bring it to the origin. But this only fixes two of the three conformal killing vectors, right? Because you have to, it's a complex coordinate, right? You fix a complex coordinate to something, it just puts two conditions. Okay. So this means that you have not fixed all the conformal killing vectors. Okay, and if you naively follow the intuition that you get from the SL2C, you would conclude that once you divide by the volume of the gauge group it will again vanish. Okay. However, here that doesn't happen, okay. And the reason that doesn't happen, okay, is because once you have fixed this point, right, and let's fix it at the origin, because that's equivalent to any other point. Okay, by SL2R you can bring it to the origin. Now we can identify what the conformal killing vector is, right? That's rotation around the origin. Okay? And that's a compact group, right? So even if you divide by the volume of that rotation group, okay, you don't get 0, right? You get a non-zero result. Okay? So it does make sense to talk about the 1-point function of closed string vertex operators on the disk. Okay? The question is, how do you calculate this? Because naively, the closed string vertex operator here will have an insertions of CC tilde, right, which corresponds to the state C1 tilde PM. But on the disk or upper half plane, right, we have to have 3 host insertions to get a non-zero answer. Is that clear? Right? We need 3 host insertions. So this answer will vanish. If we just naively calculate the 1-point function of CC tilde VM, this will give you 0. Okay. And this somehow is related to the fact that you have not fixed the third CKV, right? Because at this level, at the level of the ghost number conservation, it doesn't really know that the conformal killing vector is generates a compact space. Right? At this stage, it just counts hosts and it finds that we don't have the right number of hosts, so you set it equal to 0. So it turns out that if you have to go through the procedure a little more detail, okay? But effectively the prescription that one finds that if you want to calculate the 1-point function of a closed string vertex operator on the disk, you choose the vertex operator, we choose the state not as this will replace by C0 minus on C1 bar, where this is basically half of C0 minus C0 bar. And there are some factors for 1 over 2 pi, right? Because of this conformal, U1 has a volume of 2 pi, right? Which you will not worry about. Okay. But roughly the idea is that this is only for calculating 1-point function on the disk. That the closed string vertex operator that you use is not CC tilde VM, but CC tilde VM acted out by the C0 minus C0 bar. Right? Effectively, what this is doing, okay, is to fix the CKV. Okay? But in that process, so because you can always choose to fix the CKV, right, by fixing the rotation. Okay? And that inserts an extra ghost, right? But the effect is just a simple factor of 2 pi, right, which you will not worry about right now. Is this clear? Right? So this is a lesson that for calculating 1-point function of a closed string vertex operator on the disk, the vertex operator that you should use is not CC bar V, but acted on by an extra factor of C0 minus. Okay? So in terms of vertex operator, this basically means that you have to use half of del C minus del bar C tilde. Okay, this is still a dimension 0 primary. Pardon? Yeah. One is del C and one is del bar C theta. Yeah, but on the disk, the host number on the left and right are not preserved because the boundary condition relates left and right. Right? That's why, I mean, even if this looks like two different host numbers, it doesn't matter. They in fact give the same result at the end.
So this theta insertion, we previously have an intuitive understanding of fixing the position of the
vertex
of the
operator.
vertex.
Yeah.
So del C insertion
Is fixing the rotation. Exactly. Right. After you have fixed the vertex operator here, you still have a conformal killing vector that rotates this. Right. This del C minus del C tilde basically fixes that rotation.
So maybe identify this 0 minus 0 bar with some rotation generator or
Roughly, yes. Right. It's L0 minus L0 bar. Right. And its conjugate is C0 minus C0 bar. The corresponding operator that you have to insert is this one.
like conjugated in BRST.
Well, not in the BRST sense. It's the same sense that CC tilde. We want, so once you fix it, right? That means that you have to insert some operator so that the particular generic transformation that you are using that vanishes, right? See, every transformation has an associated C host, right? Gauge transformation parameter you associate the C host. That transformation parameter, so that C host has to be forced to be zero. So you have to insert an appropriate C here, right? Which will make that another C vanish at this point, right? So that you are not allowed to make that rotation. And then another C, right? The gauge transformation parameter is the rotation parameter, right? Corresponds to basically, if we use the lambda as the transformation, lambda minus lambda bar. If this is a rotation, lambda, if suppose lambda is that angle theta, right? It's theta minus theta bar. Okay, because that's the thing we are fixing. Okay? And that means you want the C minus C bar, okay, that particular mode to vanish at this point. Right? And that's what this C0 minus is doing. So in other words, having C0 minus basically tells us that if you put another C0 minus on top of this, it gives you 0. Right? So that C0 minus is some gauge transformation, right? Because hosts are in one-to-one corresponding to the gauge transformation. You can ask what gauge transformation parameter you are forcing it to 0, right? And that is a rotation.
C0 minus or C0 is related to rotations.
Hosts are always related to gauge transformation, right? The gauge transformation in this case is world sheet diffeomorphism, right? So if you look at the world, yeah. So the first you look at the hosts are always related to gauge transformation, right? Yeah, C hosts are, right? So take a particular gauge transformation, which is the rotation. Okay? That's some parameter. You replace the parameter by C host. That combination has to vanish at the origin, right? That combination has to vanish, and that combination is exactly this one, the C0 minus. Okay? So that's the way you see that this is what you have to insert at the origin.
This kind of a decimal required state insertion would not be acceptable in a host string. Purely host string.
Yeah, I mean you wouldn't do it anyway, right? I mean, because there you don't fix it.
Such an insertion would not be allowed.
No, not be allowed means what? You're talking about because the host number is not conserved. No, because you can have C del square C minus C bar del bar square C bar, right? That's a related vertex operator. You can certainly have that, right? It will have simple correlation functions, right? That's why you have this some nice coupling of the dilaton. But you can apply, you can allow it, right? Because we didn't put separate host number constant on the left and right. When we said that the closed strings have host number 2, right? Only the total host number is fixed.
And is this such a situation or I guess somewhere else like CKV with compact volume and
Yeah, I think this is the only place I have seen that's where it's useful.
this was not rotation but some non-compact loop, then you can't do it.
Then it will be zero basically. Yeah. Right? Then the result will be zero by volume. We know that by dividing the volume of the group, you will get zero. Right? Naively, I mean, you will see the zero because of the ghost number non-conservation. Right? It's only in the special case that we know that it shouldn't actually be zero. Right? Because the group is compact. Right? And for that, you have to make a special effort to figure out what kind of C insertions you have to have. Yes.
I'm not completely clear about what this has to do with the deep brain.
Oh, deep brain because it's on a disk. We are considering amplitude on a disk, right? And you have to put a boundary condition on the disk boundary, right? That
Is it that only in case of when deep brains are present that becomes
exactly. Because without deep brains, you will not have these diagrams in any case, right? See, deep brains by definition is something where you have a you allow open strings, right? You have a because deep brains put some boundary condition, right? And this is a disk Riemann surface with boundary, right? So this kind of diagram will only appear when the background has some deep brains, right? By definition, because otherwise you will not have boundaries of the Riemann surface.
you could have done this computation with just open.
Whenever you open string, by definition, there is a deep brain. Right? That's the definition of deep brain, right? Yeah. So D9 brain is also a deep brain. Okay. Yeah. So I mean earlier we didn't think of it that way, but now we think of that whenever there is open string, there is deep brain.
In annulus,
Yes.
is this a similar logic that annulus is well defined because we have this?
Annulus, yeah, annulus also we can do this. Yeah. Annulus also there is a B0, C0 insertion.
The reason is probably same.
Annulus also has a killing vector, yeah, rotation.
And then maybe I can say similar of torus partition. Like it
Yeah.
shouldn't be well defined, but it is.
Yeah, that is true. Torus partition function is well defined.
Reason is some compact subgroup of diffeomorphism.
Exactly. Yeah.
That's why people calculate this torus partition.
Yeah. Exactly. Right. But its physical interpretation is not completely clear. Right. What it means.
Here we have physical interpretation.
Exactly. Yeah. Because this is really the one-point function. It is telling us what kind of source the deep brain produces. Right.
1 point. Can we like think of it in terms of electromagnetism? How we can see that point particle?
Yeah. Electromagnetic. Like in the present of electromagnetic field, there is a coupling like integral d tau a tau. Right. Right. So if you calculate the derivative, the source for mu x is integral or is integral d tau delta of x minus x mu of tau, right? But this is say okay, dx mu. This is a full coupling. Okay. So this is the source. Okay. And this is along the deep brain wall and along the particle wall line, right?
Like point coupling to like some world line.
Exactly. Okay. This point coupling to some wall line. Okay. So if you calculated a 1-point function of mu, when there's a point particle moving, charge point particle, you'll get a non-zero answer. Right? Because mu of x. So you can write, basically you write as integral dx mu of x times this. Right? The same thing, coupling, you can write it this way. Right? Because x integral will basically, yeah, using delta function. So then this is the source. Right? So this is a 1-point function of mu. Yeah, so this is exactly similar. That there's a 1-point function of mu that you are calculating. Is this clear? Are there questions? Okay, so I'll describe various subtleties and then maybe the actual calculation we have to do next time. So if you look at that expression over here, right, you have some expectation value of the form C tilde del C minus del bar C tilde dm times other things, right? These are the e to the minus 5 factors. But let's just focus on this. So you see that different terms, I mean, it has C and C tilde both. Okay. So how do we calculate such objects? Okay, and you are calculating on a disk or upper half plane. Let's take upper half plane. Right? This origin can be mapped to the point I. So you have del C, so the two terms are del C, C tilde of I, and del C, del bar C tilde of I. So the general procedure for doing such calculations, okay, is to use the method of images. Okay. What this method of images allows us to do, okay, and this works not in general, right? If you have a general matter field theory, this is complicated, but at least when you have things written in terms of the ghosts and matter, the standard X, right, the flat space, okay, then you can use this method of images. Okay. And this procedure is that we take all the non-holomorphic objects and or anti-holomorphic objects, okay, and replace them, okay, by the value at their image. Okay. So claim that this correlation function can be calculated by replacing some O at say x plus iy, so O tilde, right, non-holomorphic object placed at x plus iy, by O tilde by O at x minus iy. And here there can be a plus or minus, and this depends on the boundary condition. So I'll give some example. Okay. That if we have B of x plus iy, B tilde of x plus iy, you replace it by B of x minus iy. Same for C. C tilde of x plus iy, replaced by C of x minus iy. If we have del x of x plus iy, this you can replace by plus or minus del bar x nu x minus iy. Sorry, the other way. Because on this side we are writing x bar and on this side without bar. Okay. So here the plus is for n and minus is for t. For B and C, there are these signs didn't appear because they always have normal boundary. E to the I k dot x at x plus iy. This is replaced by e to the power plus minus I k dot x at x minus I. This is not replaced, this is repeated. Again, plus for Neumann minus for Dirichlet. Pardon? Well, you pretend as if there is e to the I k dot x here. and another e to the minus ik dot x plus minus ik dot x at the image point. Okay, because this is the point, because the point is e to the ik dot x has both holomorphic and anti-holomorphic part, right? So it's basically the anti-holomorphic part which is getting replaced here. So ultimately the calculation will involve only the holomorphic part, right? Because all the anti-holomorphic parts are replaced by holomorphic parts anyway, right? If you have del bar x, right, it will be replaced by minus del x or minus del x or plus del x, right? So at the end, only the holomorphic parts of these will be important. But so this, when I say repeated, this basically means that the anti-holomorphic part is replaced by the holomorphic part, right? But you can write it as e to the ik dot x. So at the end, the anti-holomorphic part will have no role to play anyway.
By this, do you mean this vertex operator you
For the
should think
plane.
of as alpha?
At the end, you will calculate about the plane and only the holomorphic sector, right? You just forget about the anti-holomorphic sector altogether. Was there a question on that?
Yeah, I was asking this vertex operator, then you should only think of as some alpha prime k square by 4 comma 0 or like 0 comma alpha prime k square by 4 dimension.
0 comma, exactly, yeah. So everything you think come in terms of holomorphic. Right, and you do the calculation only in the holomorphic sector. Okay. And basically one can show that this produces the correct answer for the disk amplitude or the upper half plane amplitude. Okay. And the way you show it is by showing that all the OPs are preserved. Okay. You see, suppose you have an anti-holomorphic operator on the upper half plane, right? Somewhere on the upper half plane. The holomorphic operators are not going to have any OP with that anyway. Okay. So if you remove it, right, all the OPs are preserved. Okay. By putting the image, essentially amounts to imposing the correct boundary condition. Right? Suppose you are trying to calculate the del x mu correlation function. On the upper half plane, if only the holomorphic operators that are relevant for OP, right? So which are preserved anyway, which are not moving. Right? But you also have to make sure the del x mu on the boundary, right, is equal to del bar x mu, right, or minus del bar x mu or plus del bar x mu. Right? And that is ensured by putting the image charge. Okay. So next time we'll try to work out some examples, right? That's to see why this works, right? That this method of images, right, produces the correct OP and the correct boundary condition, right, with these rules. Okay. And then we are going to apply this to calculate correlation functions on the to calculate this one-point function. Okay, there is one more point I have to just emphasize, okay, because this is not the full story, because this will generate the correct correlation function up to an overall normalization. Because this preserves the OP structure, but it doesn't tell you what the overall normalization is. So this gives the disk one-point function, or in fact other amplitudes also, and other disk amplitudes. Up to an overall normalization. This has to be calculated separately, which also we'll discuss next time. Need to be calculated separately. No, it's not because of the volume of the compact group, because different D branes have different tension, right? And this calculation really knows nothing about the tension of the D brane. Okay. Because, okay, another way of saying is that we have normalized, we normalize the host correlation function on the plane by saying that the 3 C's and 3 C tildes give you 1, right? C0, C1, C minus 1, C0, C1, C tilde, minus 1, C tilde, 0, C tilde 1 gives you 1. Okay. This fixes the normalization of the C's. You can say that, okay, how do you know this is true? This can always be ensured by choosing the ghost to be appropriately normalized. Right? If it was not true, you just change the normalization of the C's, right? You can correspondingly use and change the normalization of the B so as to that BCOP is preserved. Once you have done that, then on the disk, you don't have any freedom of normalizing the C's again, right? Because you have already fixed the normalization of the C's. Now on the upper half plane, right, or on the disk, if you calculate the expectation value of C minus 1, C0, C1, you cannot set it equal to 1, right? Because you have already used up your freedom of normalization. So because of this is some number that you have to calculate, right? And this is related to the deep brain tension. Okay, so this we will see that how to calculate the deep brain tension. Right? That will require a separate calculation. But this calculation will tell us which one-point functions are non-zero, right? Or it will also tell you the ratios of the one-point function, right? If you want to calculate the ratio of the graviton one-point function to graviton one-point function, right? Then this overall normalization doesn't matter, right? You put the graviton vertex operator with the C0 minus, dilaton vertex operator with the C0 minus, and calculate the ratio.
That's supposed to be the disk partition.
Exactly, but the disk partition function is an arbitrary constant here, right? I mean, you don't know what the disk partition function is. That's what the normalization is about. Okay. So this has to be calculated separately. There is an unambiguous way to do this. Right? You have to factorize in the factorizing the annulus. Right? As a,
Same thing you do for in non-boundary Riemann circle. Like fixing the for a 4-point function.
yeah,
You should factorize into 2-3 points.
exactly. Right? So you have to use the factorization, right? If you take an annulus. So annulus, we'll see that it's unambiguously defined. Okay, because that can be reinterpreted as a trace over open string states. Right? There is no confusion. But that annulus you can also factorize into two disks connected by a closed string. Right? And using that we can figure we will be able to normalize the disk amplitudes. Okay, any other question? So then the next class will be Thursday. And I think the other thing is that I'm supposed to officially end the course on 22nd. So after that, I'll take some unofficial lectures, right? I mean, so the classes will be there, but it will not be counted as part of the course. So exams, yeah, exams will depend on only up to that point. Whatever will be covered up to 22nd. You know, 22nd also probably there will be no class, right? Because no, not 22nd. In-house, yes, sir, yeah. Yeah. Less and less syllabus, yeah.
About the term papers. Yeah. So what can I gravitate on? I had in mind something maybe to do with topological, so that's closer to it.
Okay, yeah, that is fine.
Yeah, but specifically like topological string or